Hello, dear students. A very warm welcome to this short presentation on the topic of Introduction to Euclid's Geometry. Now, this is a chapter which has a very low weightage, only 1 or 2 marks in board exams. But basically, this forms the very basis and fundamentals of the geometry that we are going to study further in higher classes as well. Topics like congruence, similarity, trigonometry, circle geometry, or anything that we'll be studying, the foundations are laid in this very chapter, and hence it is important to start with this chapter if we are going to start our study of geometry, right? Now, although this chapter is not very important from the viewpoint of exams, but it would be good if we get to understand the basics that this chapter deals with. So I am Aditya Gupta, and let's get started. So the main topics that will be covered here in this presentation are some of the very basic definitions laid by Euclid, then his axioms and postulates, and finally followed by the very important postulate, which is the fifth postulate. So equivalent versions of the Euclid's fifth postulate and some questions based on that. So, as far as Euclid is concerned, he was a very great mathematician, very great geometer in his time, and he wrote a book called The Elements, in which he was able to very systematically list out the foundations of geometry, and that's how the Elements is widely regarded as the Bible of geometry. Now, let us see what were some definitions that in the book one of the elements he stated. So the very definitions that he said was that what is a point? First of all, a point is that which has no part. So look, he was actually a Greek mathematician, so all of these are just translations in the English language from Greek, right? So a point is that which has no part. Now look, here in our diagram we have we can also define that point is a basically a very fine dot. So this basically can be called a point, or it is an exact location of anything, so that is also a point. And this is also a correct definition, which has no part. So no part means it is zero dimensional, it has no dimensions. So all of these are equivalent definitions of a point. Now, what is a line? A line is a breadthless length. So breadthless means it is a one-dimensional curve. It is a one-dimensional object, right? So that's what we mean by a line. Or in other words, we can also say that it is a straight path that goes on forever in both the directions. So basically, it never stops, right? So what we are saying is that a line is represented in this form. These arrows represent that it is continuing forever in both the directions. So that is what we mean by a line. And it has zero thickness. It is not at all thick. It is the finest line that we can ever draw. Now, clearly, we can see that a line is composed of points. A line is composed of infinite points very close to each other. In fact, infinitely close to each other. We can find infinite points on a line. We can mark infinite points on a line. So this is a very basic fact that we should be aware of. Now, what are the ends of a line segment? So basically, in particular, it is talking about a line segment. That what are the end points of a line segment? They are going to be points. So if we have, what is a line segment? First of all, here we have the very definition, part of a line that has two endpoints. So for instance, if we have a straight line and we take any 2 points on this, A, B, we name them, then this portion of the line is called the line segment, right? Of course, it will have two endpoints, A and B, which are going to be which we are saying that they will be points. So that is a very obvious fact here, very obvious definition. Now, what is a ray? A ray is a line with just one endpoint. So it is just one endpoint, but it is continuing indefinitely in another direction. So in this direction, it is continuing indefinitely, but in this direction, it is finite. It is starting from this point. So that's what we mean by a ray. Here we have drawn also how a ray is represented. Now, line segment is represented like this. This is a line segment, correct? Now, let us talk about a straight line is a line which lies evenly with the points on itself. So yeah, that's correct. Basically, a straight line is a line which lies evenly with the points on itself. It means that the points are laid out, as we have already discussed. There are infinite points on a line. They are laid out evenly. So basically, there is no up or down. They are just evenly in a very uniform manner laid out, and that basically constitutes a straight line, right? Now, what is a surface? It is a surface that has length and breadth only. It means that it is a two-dimensional object. A surface has length and breadth only, but not a height, and hence it is basically referring to the idea of two dimensions rather than one dimension. So look, one dimension was defined by a line which only constitutes a length. Point had zero dimensions. Surface has two dimensions, which is described by both a length as well as a breadth. And of course, later when we will study three dimensions, it is constituted by a length, breadth, as well as a height. Correct? Now, the edges of a surface are lines. So basically, this can be a surface, for example. Correct? A plane surface is a surface which lies evenly with the straight lines on itself, right? It means that all the lines are lying evenly one next to each other. It is not that two lines are like this, then it is not that two lines are like this here and then the third line is above. No, they are lying evenly on a surface, and that's what we are saying will constitute a plane surface, right? So a plane is basically represented something like this. This is how we can draw, correct? However, this is a plane, let's say. Okay, this we can call my hand a plane surface. A paper is a plane surface. So any two-dimensional flat surface is called a plane surface. A blackboard, the surface of a blackboard is a plane, correct? So that's what we mean by the notion of a plane. It has to be perfectly flat, and it should have zero thickness, right? So basically it has length, breadth, but no height or no thickness. So my hand actually has a little bit of thickness, but a perfect plane would have zero thickness. Absolutely, since it is only composed of straight lines, one next to each other, so it can never have any height since a line has no thickness, correct? Now, we can also see here what are parallel lines, perpendicular lines, intersecting lines. So basically, first let us talk about intersecting lines. Any two lines which have a point in common, they are called intersecting lines, correct? Similarly, perpendicular lines are any two lines which have an angle of 90 degree or a right angle in between them, correct? Similarly, parallel lines are lines that never meet each other, correct? So these are very basic definitions that we should be aware of. Now let us see what are the axioms and postulates that were given by Euclid. Now, before we even discuss about those, let us first understand what we mean by axioms and postulate themselves. Because we have often heard theorems, we have often heard about mathematical statements, proofs, but probably it is the first time that you are hearing the word axiom or postulate. So let me explain what we mean by an axiom or a postulate. Basically, it is something which is very obvious. It is a fact which seems to be self evident, very obvious fact, but we cannot prove it. So then it will be called an axiom or a postulate. Axiom and postulate are used synonymously. They both are used to mean the same thing. So you can use the word axioms also, postulate also. They are in modern times, they are used synonymously. One can replace the other, right? So they are very self-evident, very basic, very obvious facts that seem to be perfectly true, that are very obviously true, but we cannot prove them, right? So, formally speaking, it is a statement that is taken to be true taken to be true, okay? It is assumed to be true, which means that we cannot prove it to be true, okay? And it serves as a premise or starting point for further reasoning and arguments. So basically, these axioms and postulates serve as a foundation to develop the entire geometry including congruence, similarity, trigonometry, circle geometry, anything at all that we'll be developing further is completely based on these axioms and postulates. So that's what we mean by further reasoning and arguments to develop the branch of geometry, right? This comes from a Greek word axioma, so which is thought worthy or fit, which commands itself as self-evident. Now, some of the Euclid's axioms that he stated were that things which are equal to each other, things which are equal to the same thing are equal to one another. Algebraically speaking, we can say if A equal to B, if A equal to C, so B and C are equal to the same thing A. So then they must be equal to each other also. So quite a basic fact that we cannot prove, but it is so obvious that it should be true, right? Another thing is if equals are added to equals, the wholes are equal, right? So what we are saying algebraically is that if A equal to B, C equal to D, then if these equals are added to equals, the wholes are equal means A plus C would be equal to B plus D. So algebraically we can represent it in this manner that if A and C are added, it will give us the. So what do we mean by wholes? The wholes are equal. So whole basically refers to sum. Okay, whole basically, since it has been translated from the Greek language to the English language, sometimes you might find the language a little bit weird and sometimes a little bit philosophical, poetic, right? But at the end of the day, we need to understand what it means. So the wholes are equal means, so this whole thing which is being formed by using A as well as C would be equal to the whole thing formed by B and C combined together. So that's what it is referring to as whole, the whole part, okay? The whole portion basically. If equals are subtracted from equals, the remainders are equal. So it means if A equal to B, C equal to D, so these are the equals that it is talking about. Algebraically, we can say now, if equals are subtracted from equal, then these remainders or the differences would be equal. So that is also very obvious. Things which coincide with one another are equal to one another. Of course, that is the case. So if there is a triangle like this, and there is another triangle like this. So of course, if I cut this second triangle using a scissors and then try to bring it over the top so as to, so you will find that both of these triangles coincide exactly. Both of them superimpose the other triangle completely. So what we are saying is that if they coincide perfectly with one another, then of course they will be perfectly equal to each other in all sense, in every sense of the word, right? The whole is greater than the part, of course. If there is a line, this is the whole line. If you take any part of it, this part of it you are taking. So of course, this whole line is greater than the small part which we have taken. That is the most obvious thing. If you take any triangle, let's say, and you take any part of this triangle, let's say this part you are taking, so of course the area of this part will be less than the area of the whole triangle. So these are very basic things that we should be aware of. Things which are double of the same things are equal to one another. So let's say there is a quantity B which is double of A, and there is a quantity C which is also double of A. So things which are double of the same things. So B is double of A, C is double of A. So they are double of the same things, then they will be equal to each other. So of course they will be equal because B is also equal to 2A, C is also equal to 2A. So they both will be equal to each other, right? So as we said, these are very basic facts. There is nothing hard here. These are self-evident. So there isn't much to think about, right? Things which are halves of the same thing, so are equal to one another. So let's say B is half of A, C is half of A. then of course B and C will be equal to each other, correct? So that's what we, these are some of the axioms laid out by Euclid. Now let us see some postulates as well. So some of these postulates, what are they saying? A unique straight line can be drawn joining any two distinct points. So what we are saying here is that let us say there are 2 points, two distinct points given in any plane. Then there exists a unique line. Unique means only one line which can be drawn joining these 2 points. So only one single line can be drawn which joins these 2 points. Okay, so this is something that we should, which is the first postulate. And in fact, it so happens that this straight line is also the shortest, is also the curve with the shortest length between joining these 2 points. So if you join any other curve, let's say something like this, joining these 2 points, then this length will actually be greater than this line segment's length. Okay, if we draw another curve, let's say something like a triangle, okay, then this path length will also be greater than this line segment's length. So what we are saying is that this that the shortest distance between the 2 points is described by the unique straight line which joins them. Okay, a terminated line can be produced indefinitely. So that is obviously true. Let us say there is a line segment which it is calling as terminated line. Then we can, of course, if we want, we can produce it indefinitely in both the directions. Even if there is a ray, so this line is also terminated at this point. But if we want, we can, of course, produce it indefinitely in the other direction also. So very basic facts, as we said already, a circle can be drawn with any center and any radius. So of course, that is the case. You can take any center, any point as the center, and then any radius r you can take and draw a circle with that radius. It is very easy. Even we have seen using a compass that, okay, whatever radius we have to draw, we just open the compass that much, and then we draw a circle using that compass. So yeah, of course, it is possible to draw any circle with any radius and any center. All right angles are equal to one another. What are right angles? 90-degree angles. So all of them are equal to one another. What it means is that if there is a 90-degree angle or right angle here, and there is another right angle here, something like this, let's say, then they are absolutely perfectly equal. It means that they can be superimposed or coincided. They can be made to coincide with each other. So if I pick up this angle, let's say this angle, and bring it and keep it here, then it will exactly coincide with the origin, with this right angle as well. So of course, if both are 90-degree angles, they will coincide with each other. This is also very basic. So these four postulates are so obvious and self-evident that nobody really thinks much about them. That yeah, everyone thinks that yeah, this is so obvious, there is nothing much to ponder about. But now comes the fifth postulate, which has eluded mathematicians for several centuries. This was such a brilliant postulate that it actually gave rise to non-Euclidean geometries and so much research. It spurred exponential growth in the field of geometry, and which finally, and all of those research finally led to the fruit, which we today know as the non-Euclidean geometry, which we'll be looking in the next presentation. So the basic idea about talking so much about postulate 5 is that it is not obvious at all, and it has a very important it has very important consequences, right? Without this fifth postulate, we cannot develop the geometry as we know today. So what does the fifth postulate say? It says that if a straight line falling on two straight lines makes the interior angles on the same side of it taken together less than two right angles. So of course, what do we mean by two right angles? Two 90-degree angles. So how much do we get if we have two right angles? We of course get 180 degree. So it is saying if if the sum of the interior angles is less than 180 degree, then the two straight lines, if produced indefinitely, meet on that side on which the sum of the angles is less than two right angles. Okay, it is a little bit difficult to understand, so let us try to understand it better, what we actually mean by this. Look, if there is what it says, let us read it. If a straight line falling on two straight lines, so let us say there are two straight lines, let us call this L, this line as M. If a line falling on these two straight lines, this is the line falling, let's call this line N, makes the interior angles on the same side of it. So look, what we are saying is any side we can choose. Either we can choose the right side of this line or the left side. Let us say if we choose the right side, then the two interior angles that it forms with lines L and M. So of course, this is one of the interior angles. This is another interior angle. These are the two interior angles which it forms. Then the two straight lines, if produced indefinitely, will meet on that side on which the sum of angles is less than two right angles. So if alpha plus beta is less than 180 degree, then where will L and M meet? On the right hand side or on the left hand side? L and M will meet on right hand side here. Okay, because alpha plus beta is less than 180 degrees, so if they are extended indefinitely, they will meet at a point P, which will lie to the right here, because they will meet on that side on which the sum of angles is less than 180 degree. So here if we have assumed that sum of these angles alpha and beta, if it is less than 180 degree, then they will meet on the same side. Okay, here of course, if this is gamma, this is delta, then it is so obvious that gamma plus delta would be greater than 180 degree. Since this sum is greater than 180 degree, the lines will not meet on this side. These lines L and M will not meet on this side. So this is what actually the Euclid's fifth postulate tells us. Okay, so this is a very important postulate, and this is something that we should also remember. Now imagine what would happen if alpha plus beta is exactly 180 degree. That actually gives rise to parallel lines, right? And what we can say is that if alpha plus beta is exactly 180 degree, look, what we can say is that how much will be gamma plus alpha? First of all, it will be 180 degree. What will be alpha beta plus delta? It would be 180 degree, of course, because they are lying on a straight line. So now if we are assuming that alpha plus beta, if that is 180 degree, then what will happen is that let us add these two equations. We will get gamma plus alpha plus beta plus delta is equal to 180 degree plus 180 degree. So alpha plus beta is already 180 degree. So gamma plus delta plus 180 degree gives us 180 plus 180. Now 180 will get cancelled. So we will also get gamma plus delta is 180 degree. So what we are saying is that if it so happens that sum of two interior angles, alpha and beta, is 180 degree, then on the other side also the sum of the interior angles will be 180 degree, as I have proved here. So what will happen in that case? Postulate 5 tells us that the lines will meet on that side of the transversal, or on that side of the third line, where sum of interior angles is less than 180 degree. But in this case, neither side satisfies that. This side also the sum of interior angles is equal to 180 degree, not less than 180 degree, and here also it is, on the other side also it is equal to 180 degree. Then in that case what will happen? The lines will never meet. They cannot meet on right hand side, because alpha plus beta we have assumed equal to 180 degree, and then they cannot meet on the left hand side. also, because here we have proved that y gamma plus delta is also 180-degree. So on neither side we are able to get alpha plus beta less than 180, and hence they will be parallel lines. So this way we can say, let us see, this way we can say here that equivalent version of Euclid's fifth postulate also we will see here, which is the very same thing that talks about parallel lines, and hence the fifth postulate of Euclid is also sometimes called the parallel postulate. So let me write it down, sometimes referred to as the parallel postulate. Okay, fine. Now let us see a very easy question here. If ABC are 3 points on a line and B lies in between A and C, then we have to prove that AB plus BC would be equal to AC, correct? So look, here we can observe that the length AB and the length BC and the length AC, we can easily observe that AB is a part of the whole line BC, and BC is actually the remaining part. BC is actually the remaining part of the whole line segment AC. So which postulate can we use? We can, or which axiom can we use? We can use axiom 4. Look, what does axiom 4 state? It stated that things which coincide with one another are equal to one another. Here we can easily see that AC actually coincides with AB plus BC. Why is that? Because what is length AB? This is length AB. To this, if I add the length BC, of course, we are going to get this entire length. And we can observe that this entire length is exactly coinciding with AC only. Hence, since they coincide exactly, using Euclid's axiom 4, we can say that things which coincide with one another are equal to one another, and hence it can be deduced that AB plus BC would be equal to AC. Correct? And of course, here we have assumed that there is a unique line passing through 2 points. Okay, so that is already the axiom 1, that unique line will pass through 2 points. Correct? The reason it is important is because if there, let's say we did not know that there is a unique line, then maybe through A and B this line is passing, maybe through B and C this line is passing. So we couldn't, it is important to assume here that unique line passes through any 2 points, right? Fine. Now let us see the equivalent versions of Euclid's fifth postulate. As I have already discussed, it is a very significant postulate in the history of mathematics. There are several equivalent versions of this postulate. One of them is the Playfair's axiom. What does that state? It states that for every line L and for every point P not lying on L, there exists a unique line M passing through P and parallel to L. Okay, and it can also be stated in a different form. Two distinct intersecting lines cannot be parallel to the same line. This we will prove later as a question also. Here we have a question and we'll prove this using Playfair's axiom. So basically once we prove this, what are we proving? That these two are equivalent versions only. So we can say that indeed this can be stated in this form also. This will prove in that particular question which I just showed. So right now, let us just focus on this theorem. What does it say? That if there is a line L and there is a point P, then there will be a unique line M which will pass through P and it will be parallel to the line L. So what we are saying here is that this discussion that we were having here, that how we can get an idea about parallel lines through the fifth postulate of Euclid is actually being discussed there. So if there is a line L, there is a point P, what we can try to do is we can try to try to make a transversal or any line which is passing through P, and let us say if this angle is B alpha, then we should try to make a line which is at an angle 180 degree minus alpha. How would that help us? because alpha plus 180 degree minus alpha would be exactly 180 degree, in which case we know that they will never meet on any side, as we have already proved in this particular slide, correct? So that's what this Playfair's axiom is talking about, that there is a unique line passing through P which is parallel to line L. So we have proved that by this construction we can draw a parallel line, since they will not meet on any side, right? How will we prove that this is unique? We can prove that this is unique by following that. Let us say there exists another line which is parallel to this line. So then we can say that if this angle is theta, then this complete angle plus this complete angle should also give us 180 degree, and then we can prove, thus we can prove that theta will be equal to 0 degree. So of course, if theta is 0 degree, then both the lines will coincide, and hence we can prove that it will be a unique line. Although this is not really in our syllabus, but I have just told how to actually try to understand this Playfair's axiom and why it is equivalent to the Euclid's fifth postulate, right? Now let us see some questions. First question we are having here is, there exists a pair of lines that are everywhere equidistant from one another. Is this statement a direct consequence of the Euclid's fifth postulate? Explain how. So the answer would be that yes, there would exist, because any two parallel lines will always be at a constant distance from each other. What do we mean by distance between two parallel lines? The perpendicular distance between them. Okay, that's what we are talking about. So let us understand the solution clearly. That if we take any line L, let's say any line L, and we can choose any point P on this. Okay, P not on L. So let us just delete this. We are taking a point P which is not on line L. So let us say here's a point P. Then by Playfair's axiom, what we can do is we can draw a unique line which is parallel to the line L, correct? So they will basically never meet. These are parallel lines. Let us say this line is M. Now, what is the distance of a point from a line? Look, this is important to understand. If there is any line at all, and we are talking about any point A, and we are talking about what is the distance of this point from the line, it is always used to refer to perpendicular distance from the line. It is automatically understood that we are talking about perpendicular distance. Whenever we talk about distance of a point from a line, we will not take this distance. We will not take this distance. We will always talk about perpendicular distance, correct? So distance of a point from a line is the length of the perpendicular from the point to the line. So of course, if we take any point on M, P point we take or Q point we take, then these perpendicular distances will always be the same, since these are parallel lines, and hence we can say that these two lines are everywhere equidistant from one another. So that's how we can solve this question, correct? Now let us see another question which we were talking about. This question states that two lines are parallel to the same line. Prove that they will also be parallel to each other. So let us say there is a line. We will prove this by contradiction. What do we mean by that? Let us see. Let's say this same line that we are talking about is L, and let us assume to the contrary that the lines which are parallel to the same line L, let's call them M and N. Let's assume to the contrary that maybe they can intersect, maybe they are not parallel. If they are not parallel, then they will have to intersect. Now, if this point is P, then by Playfair's axiom, we can say that there will exist a unique line which is parallel to line L and passes through P. Understand once again, I'll explain very carefully. What are we saying? We are given that two lines are parallel to the same line. So let us say these two lines are M and N. They are given parallel to the same line L. Prove that M and N will also be parallel to each other. This we have to prove, okay? So what I've done is I have assumed to the contrary that, okay, somehow let's assume that they are not parallel. So then if they are not parallel, if M and N are not parallel to each other, then they will intersect at some point P. It is already given M is parallel to L and M is also parallel to N is also parallel to N. Now look, by Playfair's axiom, we can say that there will be a unique line which will pass through P and parallel to line L. Unique line means exactly one line. So this means M and N are coincident lines. They represent the same line. Why? Because both of them are passing through this point P and they both of them are parallel to line L. So Playfair's axiom tells us that any line passing through P and also parallel to line L, there will only exist one such line. So M and N must be the same line, coincident lines. But that is not possible because here we are assuming that there are two distinct lines. And hence there is a contradiction that arose out of this discussion. And hence, since there is a contradiction, our initial assumption must have been false. What was our initial assumption? So let us write this down. To the contrary, assume to the contrary that M and N are not parallel. So if they are not parallel, they will have to meet somewhere, which means they are intersecting lines. M and N are going to intersect at some point, at some point P. At some point P. By Playfair's axiom, what can we say? By Playfair's axiom, only a unique line shall pass through P which is parallel to line L, which is parallel to line L. Hence, we can write since M and N, both lines, both satisfy these conditions. What are these conditions? That they both pass through P, they both are parallel also to L. So since they both satisfy these conditions, both of these lines are satisfying these conditions, what can we say? They must be coincident or basically the same lines, right? Coincident or the same lines. But we are assuming here that these are two distinct lines, okay? So that's what we are saying. So this is a contradiction. And hence we can say that, what can we say? Our initial assumption must have been false. And what was our initial assumption? Let's see. What was our initial assumption? We had assumed that M and N are not parallel. So if this is not true, if this is false, what will be true then? If they are not parallel is false, then what is true? That they are parallel, and hence we have proved that they must be, M and N must be parallel to each other. So that was pretty much it about this presentation, and here we learned about the very basics and fundamentals of the postulates and axioms laid out by Euclid. So I hope you all enjoyed watching this lecture and learned something new. Thanks a lot for watching.